Introduction. Reinforcement learning is the fundamental problem when it comes to the getting an agent to act out there in the world in a certain manner of maximizing its rewards. For instance, consider a teaching job when you are teaching your dog a certain new trick. In this case, you are not sure and you cannot tell your dog what to do. But there is an option to reward it if it does the wrong or right thing. The dog, in this case, has to figure out what it is supposed to do in order to make it to the reward. The dog also has to learn what made him deserve that punishment as well. This is known as the credit assignment issue. Remember this example with the dog and teaching it to perform new tricks, since we can use the very similar method in order to train computers to perform different tasks, like playing chess or backgammon, scheduling our jobs and meetings, as well as controlling robot limbs, and much more. We are able to formalize the reinforcement problem as the certain environment, specifically modeled as a certain stochastic, finite state device, or machine with particular inputs. These inputs are, in fact, certain actions sent from the specific agent. Machines also come with certain outputs, as well notably rewards and observations, specifically sent to the agent. We can represent it as follows. State transition function is represented as capital P, begin parentheses, capital X, begin parentheses T, end parentheses, vertical line, capital X, begin parentheses, T minus 1, end parentheses, comma, capital A, begin parentheses, T, end parentheses, end parentheses. Observation output function, capital P, is represented as begin parentheses, capital Y, begin parentheses T, end parentheses, vertical line, capital X, begin parentheses, T, end parentheses, comma, capital A, begin parentheses, T, end parentheses, end parentheses. Reward function is represented as capital E, begin parentheses, capital R, begin parentheses, T, end parentheses, vertical line, capital X, begin parentheses, T, end parentheses, comma, capital A, begin parentheses, T, end parentheses. You can easily notice that what certain agent sees greatly depends on what it performs. In other words, it greatly reflects the fact that certain perception is an entirely active process. It should be noted that the agent is also modeled as stochastic FSM, notably containing inputs including rewards and observations, specifically sent from the environment. The agent also comes with certain outputs, like certain actions sent to the specific environment. When it comes to the ultimate goal of the agent, it is to find that policy or state update function that will be leading it to the maximizing the expected sum of different discounted rewards. We can represent it as follows. Capital E, begin brackets, capital R underscore 0, plus G, capital R underscore 1, plus G to the power 2, capital R underscore 2, plus end brackets, is equal to capital E sum underscore squiggly brackets T equals 0, end squiggly brackets, to the power infty, gamma to the power T, capital R underscore T. In this function, gamma is a certain discount factor that models that fact future reward notably less than certain immediate reward. Mathematically speaking, we need gamma to be less than 1 in order to make that infinite sum coverage. On the other hand, the environment will have 0 rewards when it comes to its absorbing states.